Reviewing the concept of division, that's the video 2.3. So reminder, if you are like, I don't remember anything about polynomial long division, please watch that part of the video tonight so that tomorrow we can practice it once and kind of work out the little things, but everybody kind of has an idea of how polynomial long division works. Okay? We're going to basically apply division to different parts of polynomials today that will be helpful for us later. So we're going to start with this lengthy mathematical definition of the division algorithm. I'm going to give you time to jot it down. And I know it's kind of a drag. I could have just put the division algorithm in my own words and made it super easy for you. But we're also getting to that level of math where we really do need to take the time to try to read what our math textbook says. Because we are mathematicians. And we need to be able to learn to talk like math. So, every now and then I must torture you with this. We'll break it down for everybody. Okay, so division algorithm, as we kind of get ready to talk about what this all means, is actually a very simple concept. So we're going to break this down and try to just make sense of what it's saying. But I'll say, okay, what grade do you think you learned to divide with remainders and things? Maybe like 4th grade, 3rd or 4th grade? Okay. The idea of the division algorithm goes back to that moment. So it's not like something that you cannot understand because you understand that about division. We're just specifically stating it, and we can use it in a lot of different cases in higher level math. So basically we're talking about two polynomials, f of x and d of x. And in the division algorithm, those are the two polynomials that we are dividing. So essentially, f of x and d of x are some polynomials, and remember polynomials have many terms that are being added or subtracted. F of x is being divided by d of x. So way back when you learned to divide, the thing underneath the division bar, this is called the dividend, the thing you're dividing. And then this, the thing you're dividing by, is called the divisor. So there are two polynomials, one's a dividend, one's a divisor. And it says, if f of x and d of x are polynomials such that d of x does not equal 0. Why is d of x not equal to 0? Because you cannot divide by 0, that's undefined. So it's just saying, hey, this polynomial is not equal to 0. And the degree of d of x is less than or equal to the degree of f of x. So we're focused on the degrees of those polynomials. Remember, the degree is just the highest exponent. So it's saying that when you're dividing by something, you've got a divisor, that degree has to be less than or equal to the degree of the dividend. So I can't take a quartic polynomial and divide it by a quintic. I don't have enough x's underneath. So I could do quartic divided by quartic, quartic divided by cubic, quartic divided by quadratic, quartic by linear, right? I can divide those things, but not if it's higher. Okay. And then the result, then there exist unique polynomials, so a single answer, q of x and r of x. And in this division, remember the answer to your division problem is called a quotient. So your q of x is the polynomial that's at the top of the long division. That's your quotient. And then you might have some r of x. I'm going to put a plus sign in between those. This is my quotient, and this is my remainder. So then there are these polynomials that satisfy this equation. So this equation is just saying, if you take your divisor and you multiply it by your quotient, and then you add your remainder, you get the thing you divided. I'm going to illustrate this very simply. 17 divided by 5. 3. 15. Remember back in the good old days when you just put R2? Yeah, okay, let's do that. And this is saying that 17, the dividend, is equal to the divisor 5 times the quotient 3 plus the remainder 2. Do you agree? Yeah. Okay. So we just call that the division algorithm. All right. That's all it says. All right, next we're going to talk about the remainder theorem. Everything in this section sounds worse than it is. Well, I guess it's good. Oh, yeah. You grow to love them. It's like those maturity thing. You know, you don't like bitter foods when you're young, but as you get older, it tastes better. That's kind of like that.
They're haters, don't listen.
I know, I'm just ignoring.
That's what teachers should do.
Mrs. Cronkey, what are you going to do about that?
She's ignoring them. They're haters.
All right.
You can't take that.
If a polynomial f of x is divided by x minus k, now it has to be a linear factor, x minus k, linear because it has degree 1, then the remainder is f of k. Okay, so just think about in this theorem, what does f of k represent? It's the y value of the function or of the polynomial when x equals k. So not only can you divide polynomials and find quotients and remainders and use the division algorithm and stuff like that, but when you divide polynomials, whatever your remainder is also the y value of your polynomial at that specific k value. So we're going to do an example and kind of like put that into context. Okay, what do you really mean by that? Here's a polynomial, 3x cubed minus 4x squared minus 41x plus 35. And we're going to divide it by the linear factor x minus 4. Since it is a linear factor, we're allowed to use synthetic division. I am a fan of synthetic division when possible because it's just quicker. So I'm going to set up my synthetic division. I don't have to worry about any missing terms, so I just drop in my coefficients. And what number goes on the outside? 4. Excellent. And then remember the little steps that we did? I just call it my little mantra for synthetic. Add down and multiply. Add down to get 3. Multiply for 12. Add down is 8. 32. Negative 9. Negative 36. Negative 1. Okay, so back it up to our remainder theorem. If a polynomial f of x is divided by x minus k, which is what we just did right there, then the remainder is f of k. So think about down here at the bottom, which one of these numbers represents your remainder? Negative 1. So that's my f of k value. K is 4, so it's saying f of 4 is equal to negative 1. It's basically evaluating my polynomial when x equals 4. The consequence of this function notation, f of 4 equals negative 1, is telling me that 4, negative 1, is a point on the graph. So it passes through that point. That's the same answer you would get if you took x equals 4 and you subbed 4 in and did what we call direct substitution. So 3 times 4 cubed minus 4 times 4 squared minus 41 times 4 plus 35, that's going to equal negative 1. But you could see, like, if you weren't using a calculator on that direct substitution, you're going to come up with some larger numbers. It's maybe not going to be as great to work with. And we were able to do it pretty nicely down here. Okay. So it's just another way to evaluate the function. That's all the remainder theorem says. Okay. Now, on a side note, I'm also going to take a quick minute to show you the division algorithm for this division problem. So remember the division algorithm is f of x equals d of x times q of x plus r of x. Okay. In this problem, that cubic polynomial, that's your f of x. That's the thing you were dividing, so that's your dividend. It's equal to your divisor, which is x minus 4, times your quotient. You're going to get your quotient down here in your synthetic. That's the terms that don't include the remainder. So times 3x squared plus 8x minus 9. Remember, they're all going to be 1 less because we divided by a linear factor. And then plus r of x, so I'm going to put a minus 1 back there. And that's basically you just writing out the division algorithm. What that means is if I were actually to go through this multiplication, distribute the x to all 3 terms, distribute the negative 4 to all 3 terms, combine all my like terms, and subtract 1, it's going to be 3x cubed minus 4x squared minus 41x plus 35. Yes. In order of operations, you should multiply before you subtract. Okay. Good. Any questions about what you're seeing on that screen? Okay, one more thing. The factor theorem. Yes. Yeah, this is going to seem very familiar to you. I know. I am too. I love polynomials. Oh, yeah. Oh, that would be really cool. Some people could do yoga, social yoga.
We should do that one thing. We should do that one thing where we put problems on the board and each group races up.
The board races?
Yeah.
I once knew a teacher, I think she taught Spanish, and someone like sprained their ankle in board races.
That's Spanish.
Yeah, this is math, so it's even more competitive.
Then I'll be going on.
I don't even care about my shoulder. I'll throw it
No,
out.
if you want to have fun, you have to be a little risky.
I know. Risk is not my middle name. All right. If I asked you what are the factors of 15, what would you tell me? 1 and 15, 3 and 5. Why are you choosing those numbers over numbers like 4 or 6? Because they divide nicely. It's divisible by that number. Your remainder is 0. So the factor theorem is still the same rule it always was. It's a factor if your remainder is 0, right? That makes sense. We'll look at an example. This example has a lot of good meat to it, different things that we can look at. So we're going to verify that x plus 3 is a factor. After we verify the factor, then we're going to find the zeros of the polynomial. Because that's really going to be our main goal here. And then f of x is x cubed minus 19x minus 30. So consider today in section 2.3, you're being provided a hint. And your hint is whatever I'm asking you to verify. So I give you a place to start. I want you to verify x plus 3 is a factor of the polynomial. If it were a factor, then f of k would equal 0. And I know I can find f of k using division. It's just the remainder. So let's divide and see if the remainder is in fact 0. What are you going to have to remember when you set up this synthetic? 0 for x squared. So 1, 0, negative 19, negative 30. And we're checking for the factor of x plus 3. Go ahead and work ahead of me and see if you can do your synthetic work. You know what it should come out to. If you're verifying it as a factor, then the remainder should be equal to 0 in the factor theorem. So add down, multiply. Oh my gosh. It works. Now some people are telling me their algebra 2 doesn't put smiley faces in zeros. That is so strange because zeros in synthetic division make me so happy because it means it is a factor, it is a 0, it is a solution. I found what I needed, right? Yay, party. Okay, so we have verified that x plus 3 is a factor of the polynomial, and now it's asking us to find the zeros of the polynomial. So does anybody have any ideas about how we might continue to find the other zeros of the polynomial? Okay, you could do another synthetic division under that. That's Eli's idea, and that's basically what you guys are going to do in 2.5 because you're going to make that list of possible rational zeros, the plus or minus p's over q's, and you'll just be like guessing and checking them. Yay. All right? But remember, I gave you a hint. It gets you started. Is there a way to do it without guessing? Dylan?
Rewrite it and factor it.
Rewrite it down here at the bottom. This is x squared, x and a number. So this is x squared minus 3x minus 10. And that's a quadratic that you could factor. If it was not factorable, you could quadratic formula. So factor this. This is x minus 5 and x plus 2. So if we're listing our zeros, we would say 5, negative 2, negative 3, the first one we checked, right? All of those are going to be zeros of the polynomial. And I'm going to go back to like Dylan's piece where he factored this at the bottom. I could rewrite this polynomial now in its factored form. It would be x plus 3, x minus 5, and x plus 2. I don't know if it's this homework assignment or one of our future homework assignments, but they ask you to write something called the linear factorization. That's that step right there. Okay, so linear factorization is just basically factored form, but the factors have to be linear. So you couldn't write it in its division algorithm, x plus 3 times x squared minus 3x minus 10, because that's quadratic, not linear. So linear factorization is when you have it completely factored down to linear values. Okay, and then the last thing, just really quickly, if I were ever to ask you a follow-up question after you find the zeros, and I were to ask you about x-intercepts, just on a side note, remember when we write intercepts, y-intercepts or x-intercepts, we're thinking about them as points on the coordinate plane. Therefore, if you were asked about intercepts, we would write them as ordered pairs. So for the zeros, if you're just asked to list solutions or list zeros, I'm okay with a list. If I ask about any type of intercept, y-intercept or x-intercept, write that as an ordered pair. All right, any questions? All right, the last thing is just a reminder, and you can choose to write these down if you want or put them in your own words. These are things you know from division algorithm, from dividing polynomials. You know the value of f at x equals k. That's equal to your remainder. You know that x minus k is a factor if your remainder is equal to 0. And you know k0 is an x-intercept on your graph if the remainder is equal to 0. So those are just 3 things that you can gather just by dividing the polynomial. Okay. Now you have a homework assignment tonight. It's like 8 questions. We have about a little under 10 minutes, but you can go ahead and get started. If your pod needs a book, send someone over to the shelf, grab a book, share it, take a picture, whatever you need to do. And I'm going to come around and check your Chapter 2 assignments. Thank you.
I had it like done and then I was asking Jayla because I didn't know if I did it right. And then can I go to the restroom real quick?
Sign out and take the pass.